Welcome to Lecture 2 for Unit 14. Today we're talking about stars, just about entirely about stars, which is a big deal because stars are arguably the most important thing in any solar system. And without our star, as you guys know, life and most of the processes on Earth would be impossible. So we're going to talk about them now. First, let's think about how we kind of organize them. So what we're going to look at in a minute on the next slide or so is this thing called the HR diagram. It's the Hertzsprung-Russell diagram. We use that to sort of organize all the different types of stars because if you didn't know, there's actually quite a wide variety of stars out there in the universe. So one way they organize these stars is by plotting the surface temperatures against their luminosity. So luminosity just being a kind of a fancy way of saying brightness, okay? So you can think about it like that. Okay? And if you've ever checked out your flashlight or actually your light bulbs, they're measured in lumens. And a lumen is just a precise measurement of just how bright a light is. So some stars are brighter than others is the thing you can imply from that. So astronomers use this HR diagram to also describe the life cycles of stars because stars actually change from their original state to a few different types of stars as they kind of live and die. So what this sort of tells us is that stars do die. They kind of run out. They have a kind of a shelf life, and this might be something new for you, or maybe you already know that. So we're going to look at these main sequence stars. So here's the diagram I was just referring to. This is the HR diagram. A few kind of actual stars are kind of listed on there to give you some reference. Okay, so here's our star we call the sun. So most stars in the universe kind of fall in this range right in here that I've highlighted. Okay, they are kind of generally that size. That's kind of the common size. So we've got kind of small to large here, and also as you notice, there's a color range, right? We've got these bluer stars, red dwarfs. We've got kind of this medium temperature yellow suns in here, and up here we're going to talk later about these supergiants, and these are pretty amazing. I have some images later to show you just to kind of like how big they are in relation to our star. They're kind of hard to wrap your head around just how large they really are. And down here, white dwarfs we're going to talk about toward the end of the lecture, which is sort of like a kind of one of the final phases of stars as they die out. So the first stage is stars start out as something called a nebula. Okay, it's a large cloud of gas and dust in space, and it's where stars are born. They're often called. You're going to see them called kind of the nurseries of stars, right? They're kind of like these large places. You'll kind of see them as these large clouds. There's an image of one coming up in a bit. They kind of look like just a collection of gas and cloud of stars, and they're really just the raw elements. There's a lot of hydrogen. There's a lot of kind of the basic building blocks of stars kind of hanging out there in space. So when the nebula is compressed, when it kind of compresses down into something smaller there, they're pulled together by gravity, right? So gravity is that force kind of pulling these particles together. So they might be really tiny, but they're large enough where they have gravity, so they get pulled toward one another. So this we know from universal law of gravitation from Newton, that gravity pulls particles of the nebula close together, right? So this is true of any particle regardless of the mass, that it's always drawn to another particle and vice versa. Okay, so they're kind of drawn together there. Oops. As what we have next is as gravity makes these regions denser and more compact, the regions spin and shrink and begin to form into a flattened disk. This disk has a central concentration of matter called the protostar. So from the cloud and the nebula, we get this sort of flattening out, the sort of kind of extension of the star kind of becomes a bit more of a shape. The protostar continues to contract, and eventually the temperature will increase over several million years. So this is not just overnight kind of thing. A star is born over a long period of time. Eventually, the gas in the region becomes so hot that its electrons are stripped of their parent atoms. So we have this stuff that's generated called plasma. All right, so these are just kind of free electrons kind of hanging out, essentially just pure energy out there in space. Not really matter per se, but just pure energy. So they move independently, and these are important for kind of the ignition of the whole thing. All right, so here's a picture of your protostar. You guys can kind of see it's kind of flattening out right there. That's the flattening of the protostar. I'm writing flattening. It's taking forever. And so the protostar sort of starts to you can see the plasma here kind of jutting out from that central thing. Almost looks like it's kind of spitting the plasma out. Next, in the longest stage of the star is the main sequence stage. During this stage, energy continues to be generated in the core of the star as hydrogen fuses into helium. So this is sort of the long life of the star. So the star has gone from a protostar to an actual star, and now it's doing its work, which is essentially is to make elements, right? So we're going to talk about how it does that in a second. So the star has a star that has a mass about the same as the sun's stays on this main sequence like we are right now for about 10 billion years. So we think our star has been kind of rolling around. It's about halfway through its life in that sequence. You know, about a little bit less than halfway, I should say, maybe about 4.65 billion years. So we've got some good life left on her. Don't worry, there's plenty of tread left in the tires of our sun. So this main sequence stage is mainly featuring nuclear fusion. Okay, so nuclear fusion is a reaction which the atomic nuclei have low atomic numbers, right, like hydrogen, atomic number 1, fuse to form a heavier nucleus with the release of energy. So this is fusion. If you've heard of people talk about cold fusion and things like that, that's us trying to kind of recreate this process on Earth. But with fusion, we've got 2 hydrogen nuclei. Okay, so 2 hydrogens that collide, and they fuse to form something called the positron. So this fusion, this kind of process, releases a ton of energy. All right, and that's essentially the energy of the sun, right? That kind of looks like a sun. As a result, you have this proton-neutron pair, all right, and that proton-neutron pair combines with another proton here, okay, and these kind of continued collisions within the core of the sun happen over and over again, and actually they start to create more heavy elements like helium. Okay, so energy is released at each step of this process. All right, and that's kind of where all the heat and light come from the sun. It's also where certain theories say all the elements that we kind of see on Earth and all that exist in the solar system are made, right? So if hydrogen, right, which is atomic number 1, I'm just going to do a quick notation there. So hydrogen with atomic number 1, if that combines with another hydrogen, atomic number 1, we've got helium, right, atomic number 2, right? And if helium combines with a hydrogen or another element, we will move on to lithium, which is atomic number 3, and so on and so on and so on, right? All throughout the periodic table. Eventually, that's how these heavier and heavier elements are created. Pretty cool stuff. Okay, so here's an image of it here. Where you guys can see the protons from the hydrogen nucleus are kind of combining, crashing together. Energy is releasing. There's positron created. And eventually, if you look over to step 3, we can see helium is created. A lot of energy is released. At every step, energy is released, which is pretty important because that's how the stars are powered. Okay, so as you leave the main sequence of the star's life, we move into the sun actually, I should say the star actually grows and becomes a giant star. So a giant is a very large and bright star whose hot core has been used of most of its hydrogen. So its hydrogen has kind of been spent up. So if we think about hydrogen as like the fuel of the star, it's starting to run low, right? The fuel gauge, is starting to go to empty. Look at that. There's our fuel gauge, right? And that'll be full. So the gauge is starting to run out here, and the star is starting to die. All right. So this is the third stage when almost all the hydrogen is used up, and it starts to actually turn a reddish color. It becomes cooler. They begin to grow into these things known as giants. All right. So stars generally aren't really born as giants, but they kind of become them, which is an important thing to understand here. Supergiants, as you can guess, are even bigger. So the main sequence stars are more massive than our sun, become larger than the giants in the third stage. So these are highly luminous stars. So remember, what does that mean? They're really bright. Okay. So these are some of the ones we can we can often see here from Earth. And these are at the top of the HR diagram. So if you look at the HR diagram again, boom, there they are. They are Betelgeuse is a famous one. That's one of the ones named long ago. But you can see these supergiants, as you can tell, a little bit bigger than our sun. Okay, I'm going to try and get you guys an image to help that a bit further here. So that might be our sun right there. If you can see that little speck down at the bottom. Just to give you a scale, I believe this is 100,000 to a million times larger when you talk about Betelgeuse and Antares, two supergiants. Just much, much, much larger. It's kind of hard to even imagine, what that would look like, with our context. Okay, so the final stage of the star, it's a little bit of a confusing term, but it's called a planetary nebulae. So as the star's outer gases drift away, right? So the star kind of has almost like an atmosphere at one point when it's a healthy kind of thriving star. It's not actually an atmosphere, but we'll call it that. Those gases kind of drift away, and the star is sort of left just to mostly its core. Okay, so these gases appear as planetary nebulae. So it's kind of like a large cloud that forms almost around the star. Okay, and we can tell that the star is dying when we see that. Okay, the final kind of the retirement, I want to call it maybe, of the star might be called is the white dwarf. So as that planetary nebula disperses, as those gases disappear, gravity causes the remaining matter to collapse inward. So they kind of condense, right, to go into something we call the white dwarf. So it's hot, it's extremely dense core of matter as a white dwarf is left. So white dwarfs shine for billions of years before they're totally cool. So if you guys know anything about like heat and colors, right, yellow is a relatively cool color, red is even cooler, blue is even hotter, and white is the hottest, right? Hear that term, white hot. That's to remind you that white, in terms of this spectrum of color, spectrum of heat, is the hottest color. So these white dwarfs are super hot. They're super condensed. All that nebulae gas, all that kind of got sucked into this middle part, and this is just as the star is about to die, kind of gets hot again and has one last fling of energy. All right, and there they are. So these are quite rare. Remember, I said most stars in the universe are in this category. The supergiants and the white dwarfs are kind of those outliers. They are not as common. So they're among, you guys can see the scale down here. This is kind of useful. So they're among the hottest here. The supergiants are among the coolest. But they're also, in terms of luminosity, they're not as bright as these larger guys. See, if you guys can see on the y-axis here, that's luminosity. They're not very bright. So some white dwarfs revolve around red giants. So these are kind of cool. There's some things called binary stars, which I think are a little bit different, where two stars revolve around on each other. But kind of the more interesting thing, and maybe you've heard of these, is called a supernova. So supernova is a star that's had a tremendous explosion that's blown itself apart, essentially, right? So that the true death of the star happens here. The explosions of supernovas can destroy the white star and destroy much of that red giant that might be nearby it as well. And of course, any other planets or other celestial objects nearby it, those can get destroyed too. It's an incredible release of energy. When we see a supernova here on Earth, we're seeing it, have happened a long time ago. So we're seeing kind of the remnants of it, because that light travels. Remember, the speed of light is really fast, but it takes a long time for that light to get here. It's so far away. We're seeing the remnants of the supernova, not the actual event in real time. And finally, when the massive stars die, they can become supernovas as well. The stars actually collapse, and high temperatures, that nuclear fusion can begin again. So the old furnace can get lit up again, so they can get hot again. That's generally just what the massive stars do. The white dwarf supernova are kind of gone, left to be some residue. Some cosmic residue, but the supernovas can actually collapse again and begin fusion again, kind of begin life again. All right, a neutron star is a star that's collapsed under gravity to the point where electrons and protons have smashed together to form neutrons. So the subatomic particles kind of change, all right, again, to become a neutron star. I believe these are quite rare, these neutron stars. So it's called a neutron star because the particles have turned back to neutrons, or to neutrons. So here's just a picture showing the whole life cycle again, kind of what are the possibilities. Remember, we start with a nebula, okay? In all cases, you go to a protostar next. Remember, protostars have those kind of flat centers there. So we can have either two things happen. One, the star can become a star like the sun, kind of your average star right there. There's the yellow star. Or it can become a supergiant, like a massive star. All right. So both of these grow throughout their life to become large, either becoming a red giant or a supergiant. And then a couple things happen, right? So as this dies, here we've got a planetary nebulae after the red giant, turning into a white dwarf in the end, or the supernova, leaving behind just that neutron star. Remember, a star that's mostly neutrons. All right, so that's sort of the two paths that stars have, both always beginning in that nursery, right? That cradle of star life, the nebula. Okay. Another thing you should know about is a pulsar. It's a rapidly spinning neutron star that emits pulses of radio and optical energy. So some Russian scientists recently have kind of captured some of these sounds because they make a radio wave that they've converted into sounds. So they kind of have played these, made these sounds. They sound quite beautiful. They're kind of like little boo, 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 pulsing sounds, which depending on the size of the star and the location of it, have different tones. And that's pretty neat. Maybe I'll show you guys that in class. But these pulsing stars kind of are another way that slowly that last stage is happening, kind of pulsing out its energy instead of just that massive release of a supernova. A black hole, kind of the last thing we're going to talk about. Black holes kind of originate with the death of these stars. It's an object so massive and dense that light can't even escape it. So massive stars produce leftovers too massive to become a stable neutron star. So some of these supergiant stars, when they die, leave us a black hole. So remember, a star has this core, right? And the core is a really dense center of matter. So the idea is that when some of these super massive stars die, they condense, like you saw in a couple examples we talked about. So as they condense, they kind of become so dense that it turns into this idea of a black hole, which is something that scientists are kind of understanding. You know, recently more and more data is coming out about them. We're actually seeing them, and gravity waves are helping us understand them as well. But we are finding them throughout the galaxy. They're out there, and we've actually just recently got our first picture of it right there. So it's about 55 million light years away in the galaxy Messier 87. So there it is right there, guys. That's a black hole. That's an image of it. You can kind of see that light around the edge of it. The actual center is the black hole. But that light around the edge of it is light being bent and electromagnetic energy being bent to be kind of pulled into it. So light gets pulled into black hole along with all matter, right? So nothing can really escape its pull. It's really an interesting kind of bend of space-time, right? My brain is not big enough to fully understand black holes, but I do have a book if you want to borrow it by Stephen Hawking, which attempts to explain it, and you can give it a shot if you want to borrow it from me. Just let me know. Hope you enjoyed this lecture, and look for some review now around Unit 14, and that is it. Signing off, Mr. Orr. Goodbye.